that have yes/no answers, which actually excludes optimization problems. So optimization problems, they return numbers, and all we are returning is yes or no. So optimization problems are not decision problems, but there's a very easy trick to turn them into that by asking if the optimum can be maximized to a certain point, i.e. can reach a certain point, or minimized, i.e. can go below a certain point. So you can turn an optimization problem into a binary search problem and make it a decision problem. But for the sake of NP completeness, the world only knows decision problems, and decision problems have yes/no answers. So what is the set of decision problems that are in NP? It's exactly the set whose yes answers come with a verifiable polynomial time certificate, i.e. the certificate can be verified or the proof can be verified in polynomial time. So only the yes answers can be. There's no such guarantee about the no answers, okay? So yes answers can be verified in polytime with certificate. This sounds really simple, but it's really powerful, especially because the no answers don't have this property. So if you somehow thought decision problems were this symmetric thing between yes and no, because yes and no are awfully similar, no. This caused me some confusion a long time ago, so don't let it cause it for you. No such guarantee. When there's a no answer, you don't have to provide proof. No such guarantees. Okay, so this is like this is sort of like, let's say you have the SAT, the satisfiability problem. You're given a Boolean formula, and you want to see if you can ever make the formula be true. Then the certificate is the assignment to the variables. But if the answer is no, the formula can never be satisfied, you're not obligated to return anything. You just say no. It can never be, okay? And as long as you're correct, no one's going to ask you for the proof in the no case. But if you say yes, you're going to be asked for a proof, right? So this is NP, right? This defines NP. And if I were to just flip yes and no, I would have co-NP. If I were forced to return a certificate for the no answers, then I'd be co-NP. And I would have no obligation for the yes answers then. But we don't really care much about co-NP. So that's the last time I'll mention it, okay? So just so that there's no confusion between the two, that's co-NP, and it's not that useful. So that's NP. Now, what does it mean to be? That's what it means. This is just what it means to be in NP. Now, what is NP hard? It is. Okay, no, sorry. First, we have to say what it means to solve a problem in NP. Okay. So, what does it mean to solve a problem in NP? It means that you can find these certificates in polynomial time too. Okay? So solving a problem in NP, let's call this, I don't know, some problem C in NP means you can provide yes, no answers in polytime. Well, it means solve it in polytime. Solve it in time t, let's say. So solve in time t. So return yes, no answers in time t. And the yeses are accompanied with certificates. And you have to obviously do this correctly. The problem has this global golden list of answers that is just like, you can think of it as enumerated somewhere in nature's book. And then your algorithm is supposed to be able to read off nature's book really quickly. So the way you do that is provide certificates that are really fastly checkable. And the no's, you don't have to do anything. Okay? So that's what it means to solve a problem in time t. If you can do this in polynomial time, then you're happy.
Can you give me an example of what one of these certificates would be?
Sure. So in the satisfiability problem, you would just show an assignment to the variables that turns the Boolean function on. Or in, let's say in the Hamiltonian cycle problem, you would just show a Hamiltonian cycle. The decision problem there is, does this graph have a Hamiltonian cycle? If you say no, you're fine. You don't have to show anything. If you say yes, you have to show the Hamiltonian cycle. If the problem is an optimization problem, like traveling salesman problem, you claim the optimum is 5. Well, then you have to show me a cycle that is feasible and has value 5.
Which is easily checked.
Easily checked. All of these easily checked in polynomial time. So it's all in the finding. It's finding a certificate that's difficult, right? Because that certificate is basically what was hidden. It's in this. Yeah, it was hidden. So yeah, again, it's best to think of a problem as a giant list of yes/no answers hidden by nature, and the algorithm's job is to just find the certificates. That's it. So that's the way to think about it. That's the best way to think about it. And sometimes it's obligated to return certificates, sometimes it's not. The times that it is yeses. Okay. So that is what it means to solve a problem in NP time. Sorry, solve a problem in NP in time t. And NP hard, what does that mean? It means if I have, let's say I happen to have a problem X, and then someone gave me a black box that said, okay, this black box solves problem X in polynomial time. Okay? Then, for that problem to be NP hard, I should be able to take any problem in NP, which is a huge class of the problems, and solve it in polynomial time using that black box. Okay? So somehow, having the black box for this problem made all of NP doable in polynomial time. That's what it means for that problem to be NP hard. Okay?
Is this NP complete? Yeah.
No, that's NP hard.
Can you say that again?
Okay. So NP hard is a problem. So if you have a problem X, X itself might not be in NP. Right? NP is a set. X itself might be some super difficult problem. Right? If this problem, however difficult it is, somehow allows you to solve all the problems within NP, you call that problem NP hard. Then, if that problem itself is in NP, you call it NP complete. Okay? So there are problems in computer science that are much harder than all of NP. You can provably show that you can solve all of NP with them and more. Those are called NP hard problems. And then there's some set of problems that are in NP that are still so hard that you can solve all of NP with them. Those are called NP complete. Yes?
Can you give an example of those problems which are harder than NP?
The halting problem. It's really hard. So the halting problem, you know what it is? No? So if I give you a the problem is, given as input another program, decide whether this program will terminate.
Oh yeah.
You can't do that in finite time. So it's super hard. If you somehow, like, from God's playbook or evolution's playbook, you could solve this problem, you could for sure solve all the NP. Okay, so that's NP hardness and completeness. Any questions? And again, this was all in the context of yes/no decisions. Optimization problems, which we're going to talk about, can be cast as yes/no problems, just by adding a binary search. Yes.
So maybe you said this already, but NP hard, is that necessarily a decision problem as well, or doesn't have to?
It is. All of complexity class world is decision problems. Most of it, sorry, most of decision class world. Every decision class we've talked about today is decision problems. Yes. So whenever you see someone telling you, oh, this problem is NP hard, and then you look at the problem's output and it's like a number as opposed to a yes or no, or it's a Tor or a circuit or whatever, there's always a way to turn the problem into a decision problem that is pretty much just as difficult. Always. And then people just don't bother with the extra step to turn it into a decision problem because that adds not much to the discussion. But in the formal world of defining NP, you have to be very careful with those. Yes?
So in the example of like a traveling salesman problem, is the question that you pose, does there exist a Tor of length blank?
Exactly, or less.
Or less.
Or less.
And then the certificate comes back.
And the certificate is the Tor.
Is the Tor, okay.
Itself. Which is easily checkable at polynomial time. You just add up the weights in the Tor, see what it is.
Yeah, okay. Yeah. Certificate is the Tor.
Yeah. Usually the certificate is the answer to the problem. Sometimes not, but usually it is.
Yeah.
So it's very trivially answered. Verified in polynomial time. Like the case that it's hard to find certificates are some primality testing problems, but we're not going to go into that. So there exist some cases where it's actually not obvious that a problem is in NP. It wasn't obvious for a while that the problem because you weren't sure whether you could return certificates that were verifiable. But then after some research, people decided. So,
but you don't have to find the certificate, right? Like you ask.
The problem, if you have an algorithm that claims to solve the problem, it must return certificates.
A quick question. So for NP, you mean we can test the certificate with in polynomial time, or we can solve the problem in polynomial time?
So this is the definition of solve. Solving means you return a certificate if you say yes.
Yeah.
But it's in NP if you can verify the certificate.
So provide the answer in T. So it's
in time T.
In time T, T is polynomial?
No, well, I wanted to keep it general because you can also solve in higher orders of time. I'm just defining what solving means right now in this board, right? Oh. This is the definition of solving. And we actually define what it means to solve a problem here because we've got so much going on. The definition is this, and then solving in polynomial time replaces T with a polynomial. Okay? So there are a lot of things you sort of hear a lot, but until they're all rigorously defined and put one after the other, it's kind of annoying to wrap your head around. Okay? Any more questions? All right, let's move on to so integer programming. So we're going to talk about approximation algorithms that use integer programming for their solutions. We're going to talk about two of them, Vertex cover and the harder approximation algorithm for the max cut problem. So we're going to see the 0.878 approximation ratio for max cut. Okay? So Vertex cover is fairly easy, and I bet you guys will be able to do it anyway. But just to make sure we're on the same page, I have to show you. So, so what's vertex cover? You're covering the edges of a graph, a regular simple graph, nothing fancy about it, with vertices. So you want to cover all of the edges with vertices. So some graph has a bunch of edges. You must pick at least one of the endpoints. So let's say we pick this one, and this one. Are there any missing edges I haven't covered? No. So we've covered all the edges just with 3. Right? So that the problem is to find the minimum number of nodes that you need to cover all the edges. And in this case, I do believe it's 3. Yeah. So then, what do you usually do when you want to write an integer program? The very sensible thing to do is to start using indicator variables as if you could optimize over them. And then you relax those integer 0, 1 variables to be real and hope for the best. And we'll see what happens here with that. So what's the objective? Let's say we have a indicator variable for every single node, whether we use it in the cover or not. Okay? Then what's the cost? It's just the sum of the indicator variables, right? So we want to minimize. So xi integer for each in 0, 1 for each node. Okay? Then we want to minimize the sum of the xi's, I going from 1 to n. No weights, right? And then we have the constraints that every edge must have at least one of its two endpoints in the cover. So then either xi or xj has to be on for all I 1 through the size of the edge set. Right? And then we had this condition that xi had to be 0, 1. So this is almost a linear program. Right? It's almost a linear program except for this constraint. Right? So this constraint we can't. So if you can't optimize this algorithm as it is because this is actually NP hard to optimize. Now, if I were to remove this constraint and replace it with simply xi is between 0 and 1, now I have a linear program because everything is linear. No two variables being multiplied together. All the inequalities have linear things on both sides. So I can solve this.
What is your I and j index in the first constraint there? You know, is I
Sorry,
and
this should be for yeah.
so okay, it's
Yeah, it's the two ends of edges. Good call. Two ends of edges. For all I n belong to P. Yes. Good. Now I can solve this linear program. I'm going to get fractional solutions. How do I? This is the difficult part of. This is the difficult. How do I round? Yes.
Every linear program can be solved in polynomial time.
Yes. Yeah. In fact, every convex program can be solved in polynomial time, and we'll see an example of that. So it won't be linear, but it will be solvable in polynomial.
worst case performance for the simplex method is not.
But that's the simplex method. There exist other methods that will solve linear programs in polynomial time. They're actually less used in practice. So, but I mean theoretically we know that it's polynomial, so we don't need to dwell on it. Okay. So now, once we have the solution to this problem, we can't just use it off the bat. We have to round, and this is where large amounts of creativity usually come into play. But in this problem, not so much, because rounding actually just means rounding. Like, you take a number, and if it's greater than 0.5, you round up to the next integer, and if it's less than 0.5, you round down. That's all we have to do here. So we're given the xi's in 0 to 1, and we round xi very simply to 1 if xi greater than a half or equal, and then 0 else otherwise. Now, why the key now is to see first of all, why is this a feasible solution to vertex cover, and second of all, how much of a weight increase did it cause? How many extra nodes am I going to use than optimum, right? So when we optimize this program, we're for sure going to get an answer that is lower than the combinatorial optimum, the true optimum. Why? Because, again, this is a relaxation. The set of things we're optimizing over is larger than the set of things in the original problem. So the answer to this, the optimal value, will be lower. But then we round it. We're going to incur some penalty for that. How much of a penalty? Can anyone see? How much of a penalty will I get if I round everything that's greater than a half to 1?
Like a factor of 2?
Yeah. Why?
Worst case, everything's at a half and you double it.
Exactly. Exactly. And sometimes we lower it, but that's just going to help. So in the worst case, everything's a half. You round everything, and you're just going to double. Right? So that takes care of the approximation guarantee, but there's one thing left. How do we know it's a cover still? I mean, sometimes we turn some nodes that were less than a half, we made them zeros. So how do we know, how do we guarantee that we're still covering every edge? This is the hard part. This is the only, and it's not hard for this problem, but it's, yes.
Well, by the first constraint, at least one of those has to be greater than or equal to 0.5. So.
Yes. So exactly. So even if for sure every edge will have one of them greater than a half. And since our rounding procedure only shot you to 0 if you were less than a half, then we're guaranteed that for every edge there's at least one node covering it. Okay? And that's it. So we just, I mean, this is the essence of almost all integer programming approximation algorithms. You somehow take your intuition from the discrete world, turn it into a program that can be relaxed, relax it, then you have the hard work of rounding. Here it was easy. Then we'll see one that is very difficult to round. Max cut is really cool to round. Any questions?
Is this the best we can do for vertex cover?
I can't remember, but I think so. I'm not sure on that, so probably. So there's one nice thing about this LP is that it's half integral. You can prove that even though the solutions are allowed to be anywhere in the real range from 0 to 1, in fact the LP solution will always be either 0, a half, or 1, which is kind of magical, but it can be proven. It's not magical. Last year we had it in a homework to prove it. So it's not a bad thing for you guys to go through and try and show for yourself. You basically show that, if you move towards either 0, a half, or a 1, you'll guaranteeably decrease the objective. So that's the way to prove this.
So does that imply that some scaling of the matrix is totally unimodular?
Some scaling of the matrix is what matrix?
Your constraint matrix on your edges. It's like almost like an infinite matrix, except they're all ones.
Times 2 minus 1
Like,
sort of thing.
yeah, but multiplying them all by 2 would be a factor of 2 to the n, right? So you need, yeah.
I hesitate to make that claim.
Okay.
But it's something like that is probably true. Okay. On to max cut. Any questions? All right. So this is a really I don't know. I like it. A really cool application of semi-definite programming. It was the first of its kind for approximation algorithms. So this was the very first time approximation algorithms were done with a semi-definite program. Okay. So you remember max cut from last time? We had the simple 2 approximation to it. A simple half approximation to it. This time we're going to get the 0.878. The problem is to just find the partition such that the cut across the partition is maximized. And it's partitioned into 2 parts. Okay? So I'm not gonna define the problem again. Maybe I should. Does anyone not remember the problem? Max cut.
Do you assume the weight is unit weight?
No. So I don't think we have weights, but it doesn't really matter. We can assume unit weights if you like, but this problem what I'm going to tell you is very easily generalized to weighted, positive weights. Okay, so I'm going to write down for a very easy solution, a very easy problem that whose solution is guaranteed to be the optimal maximum cut, but is obviously NP hard to optimize, right? So already this, you're going to ask, why did I write down this particular program? Well, the answer is that it will help us later on, and it took some creativity. Whoever came up with it first, to Gomans and Williamson came up with this first. It took some creativity on their part. So let's say every node is assigned an indicator vector, an indicator node, an indicator variable, vi, that is just a real number. And the way we're going to count cuts is by multiplying the indicator vectors together, subtracting that from 1 and dividing by 2. So if they're in the same cut, this will be yeah, it will be 0. So hang on. Oh, okay. Sorry. It's vi is -1 or 1, right? So if they're in the same, then you have 0, and if they're indifferent, so you have 1. So the weight is going to come here, weight I of j, and we're going to run through all the edges in the graph. Okay, and this is going to, so this very easily counts the number of crossed edges. That's the objective, and we're trying to obviously maximize that. The constraints are going to be that vi squared has to be equal to 1. This enforces that v is in -1 or 1. And in addition to that, that's it. The VIs are just real numbers. You'll see why I wrote this down in a second, okay? It's not silly that I said it's a real number. So the optimal solution to this problem is guaranteed to be the maximum cut, because this enforces this condition, and everything else is just faithful to the original definition of max cut. There's a problem here, is that this constraint is not convex, and furthermore, the objective is not convex. It's quadratic, but the quadratic is not necessarily convex. So 2 problems there, and we'll get rid of both of them. So another leap of creativity. Instead of assigning a single real number to every node, we're going to assign a real vector to every node. So every single node is now going to be sitting on an n-dimensional space. Okay? So immediately the VIs become vectors. So forget this. Okay? So the VIs are in Rn now. We'll get rid of this, and we'll have VI transpose here. Okay? Now, this problem, okay? This problem is a relaxation. Why is that? Well, because if I somehow knew which so if I could easily make the indicator variables sit here just as before, and so in one dimension I could just not use all the dimensions, use a single dimension, and use the indicator variables from before, and the set of feasible solutions there is a subset of the feasible solutions here, because all I did here was add extra dimensions to the problem, which seems to be silly, but it'll actually help us. Okay? So I added all these extra dimensions, I added all these extra variables, and it just kind of seems silly. I'm certainly relaxing the problem, but it still doesn't look like something that you could solve, right? I don't know. Does this look like something you could solve? To me, at first it didn't, because I was only used to LPs. And then you realize, okay, let's try and reformulate this as a semi-definite program. So to do that, I'm going to introduce yet some more variables. I'm going to introduce, call rho Pij to be exactly this right here, Vi transpose Vj. Okay? And I'm going to rewrite this program in terms of this simple renaming of variables. So this guy becomes rho ij. This guy becomes rho I equals 1. And we need one additional constraint now, right? We need the, so this program doesn't encode the fact that the Pij's have to be some products of some things. And we can put that in as a semi-definite constraint. It's exact, this constraint is, the constraint that the Pij's have to be the dot products of other vectors is exactly the constraint that says the Pij's have to be positive semi-definite. Form a positive semi-definite matrix, i.e. that the big matrix that is Pij, so this is the matrix that you fill in all the values for Pij. This guy has to be positive semi-definite. This is the symbol for positive semi-definiteness. All its eigenvalues have to be greater than 0. Okay? This ensures that Pij can be factored via the Cholesky factorization to give you the V's. So with that, suddenly this problem is a semi-definite program. And it's still a relaxation of max cut. So we've relaxed the hell out of this problem. So you think, okay, we're screwed. We can't possibly round this to a sensible solution, but we'll be able to. So any questions up to here before we solve this and use it?
Sorry, can you go over again these VI vectors?
Sure. So the VI vectors, they were originally not vectors. They were originally single numbers, in -1 or 1.
Yeah.
Right? Then we would just multiply them together. Right? But that was no good. So instead, we're going to relax by lifting them up into higher dimensions. So every single VI now is an n-dimensional vector. And the multiplications between the n-dimensional, the multiplications between the VI's and VJ's got replaced with dot products. So that's also a relaxation, because if I had it, if you gave me a solution to the original when I was in a single dimension, I could just ignore the extra dimensions that are in the VI's and use a single dimension from the VI's to recover the max cut solution.
Right, okay. So we still need to take the VI vector and turn it into a single value.
Yeah, we haven't, so for now, the rounding sounds like it's going to be really difficult, because, I mean, it's not, how are you going to take a vector and use that to assign to one or the other cluster, right? That's the sort of position we put ourselves into. It's almost like we made our life hard. But of course not.
Sorry, yes. What's the definition of semi-definite program?
Oh, so the semi-definite program is one where you're allowed to take a matrix of variables and enforce it to be positive semi-definite. So you know what a positive semi-definite matrix is?
Yes.
So then, if you have a bunch of variables and you shove them into a matrix, and then you make that matrix be positive semi-definite, this is an allowable constraint, and it's allowed, and it's convex. So convex solvers will do it. So this is the key difference between linear programming and semi-definite programming.
What's the entry of Vi or Vj? Each entry. This is a row vector, right?
These are column vectors. And the entries are to be optimized. I don't know what they're. I don't know what
So they don't need to be 1 or -1.
No. They're guaranteed to be between -1 and -1, because their magnitudes is 1. Right, but they're going to be real numbers.
So for purposes of like class and final and studying, are we supposed to know how to solve semi-definite programs?
No.
Okay.
No,
I just feel
semi-definite,
like, did I miss this part? Or?
semi-definite programs are, I mean, I've never solved one by hand other than when it's obvious. It's just like, I would be a tedious task. I would hate, I would like for you to, after this session, to just be able to write down some. But even that is probably not that important. It's just, the point that I want to make is that complex programming in their relaxation is a big push and has driven a lot of advances in integer programming. That's the point. Any other questions before we solve the problem? Okay, so let's say we now have the solutions to this problem. We have to round. So how on earth do we round? Well, consider what the VIs are. They're unit dimensional. They're unit length vectors in n dimensions. So they sit on. So let's say n was just 2. Then all the VIs are just vectors pointing in various directions. And their length is exactly 1, so they're just sitting on the unit ball. And in higher dimensions, they're still vectors sitting on the unit ball. The way we're going to round is by taking a random hyperplane and then deciding anything that's on one side, any vector that's on one side, its node gets assigned to that partition, and any vector that's on the other side gets assigned to the other partition. So sort of somewhat brain dead, but it works. So in this case, these 3 guys will be on the left, and these guys will be on the right. And that's it.
The hyperplane goes through the origins?
Yes, right through the origin. Hyperplane through the origin is going to be our rounding scheme. So that's our rounding scheme. It's certainly going to give a feasible point, so we don't have to worry about that. But what remains is how are we going to analyze the approximation ratio? That's the difficult part. And where is this 0.878 coming from? So that's what we're going to address. Well, I might as well. Okay, so I'm going to look at 2 quantities first. I'm going to look at the expected value of the cut. So the expected value of the cut, and then compare it to this. So recall that this program is going to be a larger value than the optimal value for this program is going to be larger than the optimal maximum cut because this is a relaxation. And then, but we'll effectively use this as our comparison. So 2 quantities to look at. First is the expected cut, expectation of the cut that is created by this. Okay, so there's simply going to be an indicator vector for every single edge, whether it's cut or not. An edge is cut depending on whether the hyperplane went through the angle that separated the 2. So let me make this a little bit more clear. So let's say we just had very few vectors. Then this angle theta is the set of angles that would have separated these two vertices from each other, or these 2 vectors, right? So if the hyperplane was like this, then these 2 would have been separated. But if the hyperplane was a little bit down this way, it wouldn't have separated. So the set of possible angles that would have separated the 2 is exactly the angle between the 2 vectors, theta, divided by pi, which is a half circle, right? So the probability that the random hyperplane separates 2 vectors is exactly the angle between them divided by pi. Okay, so how does that translate into our into the
Divided by pi or 2 pi?
pi?
Over pi.
Because
Yeah.
because of
Yeah.
symmetry. Yes.
What about for multiple dimensions? This is 2, right?
It's the same deal in multiple dimensions.
Okay.
So that's a little harder to see, but
Okay.
I wave my hands.
You're not going to draw it for us?
So we have the expected cut is simply the sum of the probabilities that the individual weights are cut, the individual edges are cut, right? So it's the probability that edge ij cut over all ij in E, right? And as we just said, it's exactly the angle. So I'm going to use this weird notation as the angle between vi, vj divided by pi. And that's exactly equal to arc cosine of vi, vj, vi transpose vj divided by pi summed. So now you see the cos is coming in. You might be a little less surprised about the 0.878. So this is the expected value of the cut that we'll get once we're done with our rounding scheme. But how does that compare to the optimal cut? Well, the only handle that we have on the optimal cut is the optimum value of the program, right? Oh, so instead of vi transpose vj, I'm just going to write rho. Yeah, rho ij, because that's rho ij. Okay, so we'd like to see what this number divided by the optimum is, but we don't have the optimum, so we're going to divide by this guy instead. Okay, so I can wipe this out. Wipe this out. So we'll keep that. Right? So what is this value divided by this value? That's what we care about, right? That's what the number, that's what the approximation ratio is going to be. So this number divided by this number. Wait, I forgot the weights here. You see why weights don't really matter much, because it's so easy to put them back in. So I'm just going to divide these two together and see what the ratio is using very simple calculus. Okay, so the thing that we're going to compare is how far off can these two possibly be from each other? Just this function from this function. How far off? How much smaller can this be from that? We'll find the absolute smallest ratio of this function to that function, and that will then also bound the sums ratio. Okay? So all we have to do now is, so we forget about the sums, forget about the weights. We're just going to use some calculus to see how far off can the ratio of this green guy over this green guy possibly be. And that's just 0.878, which is kind of surprising, because you wouldn't expect it. Because everything we didn't hurt the ratio so much. So the question is, what is the minimum over rho between -1 and +1 of cos inverse p of rho divided by pi divided by 1 minus rho divided by 2. And just simple calculus will give you that this is around 0.878. So the expected cut that we have divided by the absolute optimum that the optimum that the program returned is at least 0.878. Therefore, us divided by the max cut optimum is also 0.878. And that's a hell of a lot better than a half. Yes?
So this is an expectation, right? What's
Yes.
the variance of this sort of an algorithm?
It's actually very challenging to calculate the variance here. It was not in the original paper by Gomez and Williams. I just looked this up this morning. It's very challenging to look at the variance of such a thing. But you don't need it. Because to prove that it's going to happen with high probability, all you need to show is that the number itself is large. So with high probability, you won't be off by more than a constant. And that's all you care about. Because you can repeat this also a constant number of times to make sure that you're not off at all. Since you guys haven't really dived into concentration inequalities, I hesitate to show details here because it's a whole other world. Basically, you will get this result with high probability as long as you just repeat it maybe 10 times.
Can I follow up? Sure. Could you use a smart method of choosing your separating hyperplane here to get a better than expectation result?
I haven't seen one. This is the best possible thing. Like we don't have a result better than 0.878 in the general case, and this is probably one of the hottest problems in approximation algorithms and computer science in general. So if you would prove this, you would have a very nice career. So this is a very hard problem, and then you can see how much creativity it took for us to get to 0.878. And I believe the best we know we can't do better than 0.94 unless p is equal to np, and then the whole gap between that and 0.878 is open. And some people say this is the best you can do, 0.878, given some conjecture called the unique games conjecture. Which, when you assume it, then suddenly a lot of approximation algorithms become tight, in that suddenly you start seeing, just from this assumption, that a lot of approximation algorithms that have already been discovered can't be improved. And for some reason people believe it, and others are skeptics, and it's a conjecture. Same deal as with any conjecture. The jury's out. Any other questions?
So after calculating the rho ij, you can recover v, right? Then
You recover v by Cholesky factorization.
Okay.
That's how you do the rounding.
Right.
Otherwise, you wouldn't be able to do the rounding.
Okay.
Yeah, that's a good point. So once you've optimized and done your whole thing, you have just row matrix. You can't use it to round because these are the VIs. You got to do Cholesky, but Cholesky is part of the time.
Is the recovery unique, or it's up to a minus sign, or?
I believe Cholesky is unique given you have ones on the diagonal. Positive ones on the diagonal, isn't it? Okay, then it doesn't have to be. You don't need uniqueness, as long as you have some factorization.
Okay.
Yeah.
It's unique if it's Fourier.
Sorry. So I'm confused what you're rounding once you do the Cholesky.
Sorry, you're confused.
Once you have the Cholesky factorization, what are you rounding?
Oh, okay. So once I have the Cholesky factor, so what do? I get this P matrix. Then I Cholesky it to get V transpose V, and V has the VIs as columns. Right? Now, the VIs are exactly the VIs here. So this is V1, V2. So I plot these, and then I ran. So every VI is associated with a node. Right? Every VI is associated with a node. So even though it's a vector, n-dimensional vector itself, there are also n of them, and every VI is associated with a node.
Oh, I'm sorry. You're talking about how to get these vectors just to do the separating hyperplane portion.
That's how you round, right?
That
so
is
once
the
you have the
rounding.
once you have the separating hyperplane, every VI that is on the one side, its node gets assigned one partition, and every node that is on the other side, its node gets assigned the other partition.
Okay. I thought there was something else we were looking at. Okay.
That's it. And the expectation of the cut from that rounding scheme is as we analyzed.
I find hard.
There's no rounding other than that. That's already a lot. I don't know how they got this. I honestly don't. Like, to me, it's completely unclear how you would have. They need to have so much insight that these two functions aren't going to be far away from each other. I mean, what is this? Is it hard codes or something in some polynomial in rho, and then these two aren't off from each other? So let's build this whole convex program just to get there? What? I have no idea how they got this. What's up?
It's not clear that V is going to be lower triangular, so maybe we need an eigendecomposition instead of a Cholesky.
We don't care about lower triangularness. We just need a.
Okay, but we said we were using a Cholesky.
No, if you
Okay.
could, like,
That's
as
fine.
long as you could give me a V transpose V that satisfies
Yeah.
this, that's all we need.
Okay.
We don't need lower or upper
Right.
triangle.
We need a matrix square.
But Cholesky will do it. Cholesky, I mean, if you give me any positive semi-definite matrix, Cholesky will turn it into
It'll do it lower
into a-
triangular.
I don't care.
That's not going to give you the V's originally.
It will. I mean, it's.
Oh, I see, yeah.
It will give me some set of V's that I can use to round.
Yeah. You don't choose the V's off. You're
Actually,
right.
we can times a rotation matrix to V, then use very easy plane to separate this.
Yes. Yeah, we've all done a lot of linear algebra, and then it's a lot of fun, and you can do anything you want to get a V transpose V, and separate them with a random hyperplane. And uniqueness doesn't matter. Nothing matters other than the factorization. Okay. All right. I won't keep you long this time. Pizza. Any questions? No. All right.